Hey everybody, in this video we're going to be talking about concavity, but without the use of the second derivative. That's right. So we're going to examine concavity both through identification and by using average rates of change. Some pretty cool stuff. So let's dive in. Here we have a graph of a polynomial function, I believe is of degree 3, and I highlighted here this thing called an inflection point. To relate this to our everyday lives, we could say this is the mood change of the graph. So we can see here on the left-hand side that the graph is in a sad mood. It is literally frowning at us, like when we frown. So we say this graph is, on this interval, is concave down. And then over here on the right-hand side, the mood changes, and it is all of a sudden happy. It is smiling at us. It is concave up. So identification is pretty straightforward. And there could be more than one interval where the graph is concave up or concave down, but for this first example, we're just going to be pretty straightforward. One interval of concave that's concave down, one interval that's concave up. Let's take a look at this a little bit further. I dissected this graph into two sections. First section is on the concave down interval, and then over down here on the concave up interval. Let's take a look at the graphs on the concave down intervals. Here we have a secant line drawn in on the concave down interval. It has a pretty steep positive slope. As a reminder, remember, a slope is a rise over run, right? And this graph, this slope is positive. And as we move to the right, it's the secant lines are getting a little bit more shallow, which means that they are decreasing in value, right? And then it gets even smaller, less steep, and then it gets even less steep here, and then to the point where we have now a negative slope. So we go from large positive slopes to gradually smaller and smaller and smaller. So we can generalize this by saying that when a function is concave down on an interval, the rates of change are decreasing. And formally, we could say that to align with AP pre-calculus, when the average rates of change over equal length input intervals are decreasing for all small length intervals, the graph of a function is concave down. And now down here, we could see we have the concave up interval, the 5 different graphs. And here we start off with a shallow negative, so it's a bit of a bigger negative, but still it's negative, so it's small, right? Then we go a little bit to the right, and we have a secant line with a shallow positive slope. So now we're getting a little bit bigger. We're getting even bigger because this line is steeper than the previous one, so it's a larger positive, even more steep, larger positive, and very steep, the largest positive. So we could generalize here and say that, as we can see from above, when a function is concave up, the rate of change is increasing in value, okay? And then formally, we say that when the average rates of change over equal length input intervals is increasing for all small length intervals, the graph of a function is concave up. Thanks for watching.